Dr. Surjit,
Yes, please.
if you can switch off your video, then your recording will be more smoother.
Okay, okay. Let me do it.
Yeah, thank you.
Sir, may I start?
Yes, Swati, start.
Welcome to session 2 of day 6 FDP on recent trends in frequency selective surfaces for 5G and 6G applications. We have Dr. Surajit Kundu sir as invited speaker of this session. Sir is currently serving as assistant professor in Department of ECE NIT Jamshedpur and has also been associated with NIT Sikkim. Dr. Surajit Kundu sir has made a significant research contribution in the area of antenna engineering, ultra-wideband system, frequency selective surfaces, and GPR. Along with the teaching experience, sir has actively involved in the cutting-edge research development. We are very much honored and warmly welcome our invited speaker, Dr. Surajit Kundu sir, in this FDP. And now, may I request the sir to kindly take over the session and enlighten our participants with your technical talk.
Yeah. Thank you, ma'am, for this very brief introduction.
Welcome, sir.
Actually, I'm thankful to organizing team for inviting me for this in this beautifully organized E and ICT program. So let me assure that well, my screen is visible. Kindly confirm it once again so that I can start it.
Sir, actually, your voice is flickering.
Okay. Okay. Am I audible now?
Yeah, you are audible, but your voice is
Okay.
sometimes
Let
it
me
gets flickered.
please kindly allow me 2-3 minutes to join from my laptop. There might be some
Okay.
issue in the desktop.
Yeah,
So
sure.
okay. Thank you.
Thank you.
Okay, sorry for the delay. Let me share my screen first. Uh, okay, kindly inform, am I visible and audible properly?
Yes, sir.
My
You
screen
are
is,
audible,
yes,
sir. Yes.
and my screen is properly visible, right?
Yes, sir.
Okay, thank you. Thank you for the confirmation. So without any further delay, I'm starting my session. So I'm really thankful to MNIT Jaipur, Professor Singhal, Professor Renu Kumari, and the organizing committee of this E and ICT program, recent trends in frequency selective surface design for 5G and 6G application. Today I'll be delivering my talk on recent trends in frequency selective surfaces and meta surfaces for modern wireless technology. Just to begin with, okay, just to begin with, actually I don't know what is the issue. It is not allowing me to change the slide. Let me check
Okay,
it.
you
Okay,
in
okay,
that
yeah,
case,
now it is working. I think now it is
yeah,
working.
yeah.
Okay, okay. To begin with, just I'm willing to share you that where I am at present. So I'm working at NIT Jamshedpur. So it is a very small state, Jharkhand. It is situated in a very small state, surrounded by Odisha, Bengal, and Bihar. So this is our premises, the campus, and these are some places of interest in and around Jamshedpur. So this is Jamshedpur is basically an industrial area. So we are lived around 2,500 MSME and 6-7 big industries, including Tata Groups, RSB Groups, and we are having some key tourist attractions, some lakes, some temples. Some famous authors used to spend their life here, like Bhutibhushan Bhushan Bandyopadhyay. Those who are Bengali, they might be knowing him, and also all of you know about Satyajit Ray. So Satyajit Ray's first very famous film, Pather Pachali, was actually based on his literature. So his house is also very nearby, only 45 kilometers from here. And we are having some sanctuaries, wildlife sanctuaries, these kind of things in and around Jamshedpur. So I welcome all of you to visit here in any program and in any event, and we'll be happy to host you. Okay, so let me acknowledge my team members. So I'm thankful to all my co-authors and my scholars who have completed their PhD or who are pursuing their PhD with me, and also the project staffs in their various role like GRF, SRF, or project associate, project assistant. So I'm thankful to all of them. And also, I'm very much thankful to my collaborators and funding agencies for providing me the required funds for to carry different projects and research works. So at present, I'm running 5 projects as a principal investigator, and these are funded from TechSmin, ANRF, then MSME, Jharkhand Council of Scientific and Technological Advancement, BST. So I'm thankful to all of them. Okay, so to start with, let me discuss a little bit very basic first about metamaterials, metasurfaces, and FSS. Then I'll be discussing a little bit about the modern and futuristic wireless technologies that we are targeting in our work. And after that, I'll be presenting some case studies that what we have done. So 3 patent granted works I'll discuss here that their objectives and the design procedures, outcomes, these things will be discussed. And a few other topics, if time permits, I'll be happy to discuss. So all of you know that frequency selective surface, any kind of partial reflective surfaces or meta surfaces, which are buzzwords nowadays, are actually comes from metamaterial. So metamaterial is basically comes from a Greek word meta, which means beyond, and from Latin word materia, that means material. So it is basically an engineered material which is not available in
real life that can be engineered to change its property. Uh, so it's basically an assembly of multiple elements that are fashioned from different composite materials such as metals, or it could be based on plastic as well. So these materials are usually arranged in a repetitive patterns and in a scale that are smaller than the wavelengths of the phenomena that is influencing these materials properties. So metamaterials basically derive their properties not from the property from the base material, but also from basically from their newly designed the structure that the engineers are developing. So it depends on the various shapes, geometry, size, orientation, and the arrangement, placement of the unit cell. So all this can have some effect on the performance of the metamaterials. And what it can do, it can actually do multiple tasks, like it can block, it can absorb, it can enhance the uh, passing signals properties like radiation property, it can bend the signal. So it can give multi-dimensional task is possible to perform using metamaterials as per the design phenomena and as per the physical performance. So uh, the metamaterial, it can be, as you can see in this first figure, it can be classified into different parts. First one is the double positive materials or DPS materials, so which is the normal materials where both epsilon and mu are positive. Then we could have single negative metamaterials, like where either epsilon negative materials that is in the second quadrant, or in the fourth quadrant we are having mu negative materials. And when both epsilon and mu both negative, that is in the third quadrant, we can consider as a double negative metamaterial. So uh, basically the equations and these parts we usually discuss in detail in the classroom lecture. So for the time being, I can skip this part. Uh, okay, so if we move to the next slide, so we can find out the main difference between the normal dielectrics and the metamaterials. So it can be observed that when the waves are when the waves are coming obliquely at the interference of any two media. Now from this figure, you can check that the behavior of metamaterials, the normal materials in case of oblique incidents. So the light is refracted on the same side of the normal when as of the incident light in case of metamaterial. Whereas in case of normal dielectric, the direction of the refraction of the light will be in the opposite side of the normal. So this is one characteristic that can be identified in case of metamaterial. So similarly, we are having epsilon negative metamaterial, mu negative metamaterial that I have included in the first slide also. So PBG metamaterials, that is the photonic bandgap materials. So it can be properly designed. It is based on the properly designed photonic crystals that have the capability of the prohibiting um, the electromagnetic wave propagation. So it can allow the wave propagation only along the defined direction. Such kind of artificially fabricated structure are known as PBG that can control the propagation of electromagnetic waves. So it can control the propagation of electromagnetic waves, and these things are widely used basically for integrated circuits, microwave filters, where sharp selectivity, and navigational antennas like GNSS antennas. So uh, if you see this figure, the different region of the operation of periodic structures are given. So here in the first region, uh, actually that is a quasi-static region. When the wavelength is much larger than the periodicity, then the operation of the material is in the quasi-static region or in region 1. So we can apply the traditional mixing equations to obtain the parameters like mu and epsilon. In the second region, the periodicity is still smaller than a wavelength, but scattering is the main capability of resonance here, and it exhibits the abnormal properties which are not actually really available in nature. So it can obtain negative permittivity and permeability. such materials we are naming as actually metamaterials. So different kind of metamaterials are possible, like a double negative that we have already mentioned. So it could be grid of conducting wires as it is shown here, or it could be split ring resonators. It could be mushroom shaped structures. It could be slotted structures. So SRR is obviously one very old and one of the most popular structure to construct any metamaterial based surfaces. And so let us discuss a little bit about meta surface, then I will come to FSS. So meta surface is basically uh, it is very ultra thin resonating elements, and it is also considered as a two-dimensional metamaterial. So it is basically typically composed of sub-wavelength structures like meta elements, which are arranged in a two-dimensional plane. And it enables the control over the propagation as well as scattering of electromagnetic waves in the sub-wavelength scale. And it can be done by adjusting the phase, amplitude, or polarization of the light wave. So in electromagnetics, the metasurfaces basically modulates the behavior of electromagnetic waves through the specific boundary condition, uh, not through the constitutive parameters like refractive index, which we have seen in the three-dimensional space. So that is very common in case of natural materials. Metasurfaces, as I mentioned, it can be considered as a two-dimensional metamaterial or a two-dimensional counterpart of metamaterial. So metasurface and FSS is having a specific difference in terms of their physical dimension. So when the thickness we are considering less than lambda by 10, then actually it is considered as a metasurface. So now different type of meta surfaces are obviously possible. We'll be seeing some of them, and it can be applied for different purposes like polarization conversion, gain augmentation, and there could be different type of partial reflective surfaces as well, apart from meta surfaces like artificial magnetic conductor, frequency selective surfaces. Then Fabry-Pérot cavity is another possible design. So that can be used for dynamic tuning for different frequency ranges for the requirement. Uh, so these are various options we are having, but specifically in my work, I went through using mostly meta surface or frequency selective surfaces. So let us discuss a little bit about frequency selective surfaces in my next slide. So frequency selective surface is basically a periodic array of metallic patches or a periodic array of apertures that can be seen within a metallic screen. It can be either standalone or it can be printed on a dielectric substrate without any ground plane. So if the unit cell dimension of FSS is comparable to the resonating wavelength, then the patch type of FSS exhibits the response of a bandstop filter, and the aperture type of FSS exhibits the behavior of a bandstop filter. So FSS can be termed as a wireless counterpart of the traditional filter. So it is having different applications, starting from electromagnetic shielding, as a polarizer, absorber, RFID, clocking application, radomes application to reduce the radar RCS. In satellite communication, it is also having some application, and it could have different geometrical shape, like simple strip kind of shape or Y kind of configuration. So these are centrally connected configuration, basically plus shaped strips, or we could have looped elements. We could have a different patch, solid patch type of shapes. Different geometric shapes can be considered to develop the unit cell of FSS. Or we could have hybrid structures like Jerusalem cross shape. So these are all possible different kind of shapes of FSS. So here you can see some possible application of FSS. So it can be used as a self-reflector, especially in case of multi-beam applications or in satellite communication application. It can be used for used as a radome to preserve the to secure the communication. Then uh, we can use it for gain augmentation. We can use it for military applications. So there are different possible applications are there in FSS. Now let me define a little bit about some modern and futuristic technologies where we'll be designing the antennas, FSS, metasurfaces to address such applications. So just the basic parts, I'll take 10-15 minutes to discuss it. So if you consider the wireless scenario, the cellular wireless era that was started around after 70s or 80s, what we will be seeing that it was started from primarily from voice communication was the main purpose. Then in 2.5G, the data communication was evolved. And then in 4G, there was a groundbreaking work that voice over IP was first time implemented. So if you move from one generation to another generation, what we'll be seeing is that data rate is always improving and latency is getting improved. So the delay is getting reduced. So the time frame, it is basically 7 to 10 years to jump from one generation to another generation. Obviously, it depends on the market demands as well as the industry requirement, whether it will be beneficial for them or not. They will be taking a decision based on that. So, and one surprising thing we have observed that whenever the even number of generations are coming, there is a groundbreaking involvement is there. So that's why government of India already jumped towards the 6G implementation and 6G deployment. And there was a very beautiful documentation was, published by our Honorable Prime Minister in March 23. That is the 6G Bharat Vision document. So that you can download and go through it. So already, apart from that, 100 5G use case lab was also provided by DOT to different academic institutions. So NIT Jamshedpur also got one such 5 crore fund to set up the 5G use case lab. So government is investing money and we need to take that benefit fully to work in our domain. So, so 5G, it is basically a complete transformation because previously it was a homogeneous and heterogeneous separate connectivity. We are actually looking till 4G. And when we are calling from 5G, the true 5G actually gives us the advantage of connected or networked society. So in a society, networked society means everything and every element, not only human to human, there will be machine to human and machine to machine connectivity will be there. And three broad aspects are there behind 5G. And these three broad aspects are enhanced mobile broadband. So enhanced mobile broadband gives some applications like augmented reality, virtual reality, mixed reality. Then mission critical services like telemedicine, automated vehicle communication, automated UAV or drones. So everything is possible after true implementation of 5G. Remember what we are getting nowadays, that is frugal 5G. So complete 5G can gives us these advantages. And not only 5G, beyond 5G, obviously, we are looking for nowadays. So massive IoT, industry automation, everything is correlated with the 5G mission and the beyond 5G 6G implementation. So if I summarize the different applications of 5G, you will be getting that it is having a diverse application from augmented reality, virtual reality to autonomous transportation, healthcare management, then security purposes like drone and radar, automated radars and drones, smart agriculture, smart cities, then industry automation. So everywhere, it is possible only because of the 5G, true 5G implementation. Now 5G spectrum, I can skip this part. You can get two broad spectrums are actually considered. One is the sub 6 gigahertz, that is up to 7.2 gigahertz. So that is FR1, frequency range 1. And the second one is the frequency range 2, which is started from 24 gigahertz. So primarily the mobile communication or the voice communication is actually the companies or the service providers are concentrating on the FR1 bands. However, if you go to the research domain, FR1 is almost, it is oversaturated. So most of the works nowadays are done in the FR2 band, and there are V band, W band. These are actually beyond 5G. Also, we are considering those bands, even in sub terahertz or sub millimeter wave range. So if we talk about 5G, these are the key components behind 5G, like millimeter wave communication, green communication, SDR, cognitive radio, cooperative communication. So I don't have time to discuss all of them, but I'll discuss a few of them where I have developed some solution. So MIMO, you might be well aware of the multi-input, multi-output antenna systems. So you can think it very simply, like we are having both the ears, and instead of utilizing both of these, if we utilize only one, then what will happen? We'll be getting obviously some signal, we'll be receiving the audio signal properly, but the clarity and the detection will be little more difficult compared to when we are utilizing both the years. So similarly in MIMO also we are using multiple antenna systems. So one can obviously ask that in smart antenna also we are using multiple antenna systems, but the basic difference is that in smart antenna we are not having the advantage of MIMO, the two critical advantage. One is the spatial diversity and the spatial multiplexing. So these two are the main advantage of MIMO you are getting. Uh, Now, this is the MIMO system model. So you can look, if you consider this system model, what you will be getting, that at any reception point for antenna 1, let it be, if your received signal is Y1, that will be, if you multiply these two matrices, what you will be getting H11 X1 plus H12 X2 plus H13 X3. So this is gives you the spatial multiplexing. So in any particular received signal, we are having component of all three transmission. Now, instead of three different symbol, if you transmit the same symbol three times, x1, x2, x3, all are same signals, then what will happen? Then that will gives you the spatial diversity. So MIMO can employ both spatial diversity as well as spatial multiplication. So that is multiplexing. So that is one great advantage of MIMO system. And obviously it improves your capacity. So, because if the normal Shannon formula, you know, that is C equal to B log to 1 plus SNR. Now, if you utilizing multiple antennas at the transmitter and receiver side, it improves your diversity order. And by that diversity order, you need to multiply the capacity. So you'll be getting a much improved capacity in case of MIMO. So it can overcome the barrier of Shannon capacity, and it can give much more capacity in your system. Okay, so these are the advantages we have discussed. The main two advantages are spatial multiplexing and spatial diversity we have already discussed. And massive MIMO is the upscaling of the MIMO system. So whenever we are using multiple antennas, like in the order of 2, 4, 8, something like that, that is called MIMO. But when we are improving it, like in a scale of 256 or 512, that is the massive MIMO. So obviously massive MIMO is more implementable or deployable in the base station scenario. So base stations are actually considered for massive MIMO implementation. Uh, the second technology that I'll be discussing very briefly, that is the ultra wideband technology. So a signal is called signal bandwidth is will be considered as ultra wideband. From Federal Communication Commission's definition, it is when it is more than 500 megahertz in terms of absolute bandwidth, or more than 20%, 25% more than center frequency in terms of fractional bandwidth. However, in reality, we are getting more than 100%. And then if it is more than 150 or 200% bandwidth, then we are calling it super wideband also. So actually, in initial days, like of electromagnetism, like in spark gap emitter experiment of Harge and those scenarios, the Jesse Bose millimeter wave display, uh, this time at that time the communication was in UWB range, but obviously we do not have transmitter receiver proper designing the VLSI and DSP processor comes into the picture after 2010. So UWB again gained some popularity in that scenario, and in 2002 FCC provides a huge spectrum, that is from 3.1 to 10.6 gigahertz as unlicensed band. So that also gives some boosting, but obviously within that range there are so many other counterparts. So that's why, to avoid the interferences between the similar bands, FCC allows a power mask. So the UWB maximum power spectral is minus 41.3 dBm per megahertz. So that's why it is very short distance communication it is possible, because if you convert that value, you'll be getting some 0.0 milliwatt, 0.01, something like that. So it is a very small value we'll be getting. So it cannot be considered for a long haul communication, obviously, or outdoor communication, obviously. Then we'll be discussing a little bit about cognitive radio. So cognitive radio is a contemporary concept that was developed by Joseph Mitola during after his PhD. During his PhD, he developed the groundbreaking work on software-defined radio, and after that, he has given the concept of cognitive radio. So let me discuss not from the textbook or concept, just from pictorially. I will try to explain it very quickly. So suppose when we are planning to go outside, our first expectation is that obviously I will be the only one in the road. I can go very smoothly. I can drive my car very quickly. So that is our expectation. But we are in India, which is a having very high population density. So we'll be stuck in somewhere here during, especially in a celebration or any uh, occasion. So we'll not be getting any path very easily. So that is the reality. And the same thing has happened in case of wireless segment also. Day by day, new technologies are including. Some network connectivity access is there. Okay, am I still audible? Can anyone please assure me?
Yes, you are audible.
Okay, thank you, sir. Okay, so when we are actually comparing it with our real life scenario, the spectrum is also very highly congested. So if you think the solution, that is obviously the dynamic spectrum allocation and intercooperation between the different application as well as different technology. So if we are moving, if you consider this picture, when we are moving through a lane, uh, a morcha is going on in a particular lane, and these people of this lane are not authorized to jump into another lane. But there are some smart people. What they have seen, that no car or nothing is there in that road. That road is completely empty. So they just jumped in that lane and try to go fast. So that is the concept of cognitive radio. Because in realistic scenario, let me put some realistic figure in my next slide. Okay. Okay, so if you see this figure, that was a very old figure, more than 20 years ago, the experiment was conducted. So at that time also, if you consider the available spectrum and the technologies plot, you'll be seeing there is no white space is available. That means there is no spectrum is available to welcome new technology. But we cannot say ki invention need to be stopped because we do not have any more spectrum to allow new technologies. So then this is the allocation. But if you go for the real utilization, what you will be seeing that in real utilization, for a particular spectrum, over a particular duration, it can be seen that only some fraction of time were actually utilized, and other time it was the channel is completely available. Same thing happened in another experiment in the city of Barcelona. It was seen also a very small fraction of time actually the channels are occupied by the user. Other times it is unoccupied or it is completely available to utilize for any other users, by any other users. So it gives the concept of cognitive radio, where it says that without disturbing the primary user, a new technology or a new user of a different application or a different technology can occupy that available spectrum. So that is dynamic allocation of spectrum and a cooperation between the different technologies or different application is gives the idea of cognitive radio. But to implement it, we need to adapt. We need to adapt few things, like we need to adapt the channel properties. We need to adapt the system parameters. Then only the spectrum sensing can be done properly, and then only this allocation to the secondary user can be done properly. So there are different model. I am not going into much detail because obviously my main focus is in the antenna design. So let us start. Allow me to skip this part. If any one of you are interested, we can discuss it later on. Okay, so the third technology that I'll be discussing very quickly, that is the ground penetrating radar. So ground penetrating radar is basically a scanning tool, non-destructive tool, which can be used to identify any buried objects, metallic mostly, non-metallic can also be detected. So if you consider some recent applications of GPR, specifically from Indian perspective, one is the very famous Ram Mandir controversy, where the ASI actually utilized GPR to detect whether there was any old construction was there or not. That is one example. Then all of you know that around 2012 or 14, ISIS occupied a territory, that is Syria, Iraq territory, and a Kurd territory they have occupied. And that time, 14 Indian nurses from the state of Kerala, they were there, and they were missing. So after almost 1.5 years, the detection was started using GPR in that sand region, and then their dead bodies were identified. So using GPR. So these are two recent, very famous utilization of GPR I can remember now. Now, if we go through the construction of GPR, it is having basically three prominent unit. One is the source unit where signal is generated. The second most important unit is the antenna unit, and the third one is the signal receiver as well as processor uh, to display the graph. So it works on a very basic fundamental physics. Like when signal is traveling through free space, we know that it is the speed of light, c. But when it is propagating through a media which is not free space, that media is having some dielectric constant that is different from the air. So at that time, the velocity becomes c by root over epsilon r, where epsilon r is the permittivity of that media. Now, when the wave is traveling through the ground surface or the earth surfaces, obviously it will be having some particular velocity. Now, whenever it will be hitting some another object which is having a different permittivity, obviously its velocity will be changing. So, if you compare the traveling time, two-way traveling time, going downwards and reflected wave. So, if you compare the traveling time of the signal, uh, when object is not present, the time will be different, and when some another object is present, then because of change in velocity, the traveling time will also be different. So by calculating these two changes in the traveling time, the GPR system can identify some shape that whether any object is present there or not. Obviously, there are two particular parameter of antenna is actually defining that what should be the performance of GPR. One is the antenna bandwidth coverage. If the antenna bandwidth is very high, it actually helps to improve the GPR resolution. So if resolution could be of two types. One is the depth resolution. Depth resolution means up to which depth your antenna is capable to detect the buried object. And second one is the lateral or pan resolution. So what is that lateral resolution? Suppose you are having two different objects closely allied together. Now, whether your GPR system can identify that these two objects are different, or their GPR is detecting both as the same object. So that gives you the idea of lateral resolution. If the resolution is good, then obviously GPR will be able to detect, okay, although they are closely placed, but they are different object. So this both the resolutions are actually improved if we can have a wide bandwidth antenna system in the GPR. Second thing is that antenna gain. So we need to improve the antenna gain also, because if gain is improved, it gives a boost towards the down towards the radiated signal through the ground. So obviously its penetration will be improved. The third important factor is the antenna's dispersion characteristics. So if the group delay is constant, that is flat, the flat is considered like if it is the variation is a plus minus 1 nanosecond. Second thing is the its a magnitude response as well as phase response of the antenna transfer function of that means S21. If that is also varying linearly, then we can say that dispersive effect will not be very much in case of your antenna as well as GPR. So that is also important to keep the constant group delay and linear phase variation of the antenna, so that our signal will not be distorted that much. Then another GPR significant effect is the ringing effect. So we need to also reduce the ringing effect, and ringing effect is mostly seen in case of impulse radar. So what is ringing effect? Like impulse radars are basically working by triggering through a short narrowband pulses. So if the short duration pulses might be having some on time and it will be having some off time. Now on time is very small because it is its pulse duration is half nanosecond or picosecond, and off duration will be high. Now, ideally, your GPR or any impulse radar should work only when the pulse duration is on time. During the on time only, it should work. But because of the ringing effect of the antenna, it can work even if the pulse is off state. So that is called ringing effect, and it can be reduced by including resistive loading in your antenna design. But there is a limitation also, because if you incorporate the resistive loading, then it will reduce the efficiency of the antenna. So obviously we have to find out some solution based on the application and design strategy, so that ringing can also be minimized. So these are some fundamental discussion, and GPR can be used for many purposes. This part I have already discussed the characteristic of the GPR. Let me tell you that why I have focused on MIMO antenna and UWB antenna, especially for recent and futuristic communication applications. Because this is if you consider this figure, so basketball is something or NBA is something where height is a factor, and you cannot improve your height just by taking some medicine or something like that. So it is somehow inherent in our genome. So if you compare, both the players could be very good, but one player is having very good height, so obviously he is having some added advantage. Similar to MIMO and UWB, both the technology in, is having some inherent advantage to work with very high data rate, because in 5G or beyond 5G you are targeting the Gbps data rate. So you can achieve it using both the technology. In case of MIMO, if you are using a 8 MIMO system with a massive MIMO system with a diversity order of 512, we are getting a capacity that is close to 1 Gbps, and for QAM modulation, 8-bit QAM modulation. And similarly for UWB, if you are having a 5 gigahertz bandwidth, and if you are using a QPSK modulation for single antenna system, we are getting 1 Gbps connectivity. But obviously in this case the chances of distortion is much more. The reason is that 5 gigahertz bandwidth, that is much more than the channel coherence bandwidth. So obviously there will be chances of distortion will be more, intersymbol interferences chances will be more. Now let me present some case studies that we have done in our laboratories for some research projects. So the first one is the a MIMO antenna that you can see here. So this antenna design is begins with a quadrant shaped patch over a 10 mm by 10 mm Rogers substrate, RT-Duroid substrate, and the patch radius is basically set 4 times that of a circular patch. And to improve the impedance bandwidth and to ensure the operation at the targeted 5G, the ground plane was actually reduced ground plane, and the alternating current distribution and the electric field, all the parameters were verified. And then we have tuned our design properly. And then it was placed in this configuration to develop a 4x4 MIMO configuration, quad port MIMO configuration. And the gap between the elements were also optimized, and this diagonal shape, the ground need to be shorted in case of MIMO. So this diagonal shorting is done there. And what we have achieved, we have achieved a bandwidth coverage for all the ports, that is in the FR2 bands. So that is around 24 to 31 gigahertz. And we are getting usually antenna interport isolation that is below 20 dB. So maximum minus 20 dB in the bandwidth. During the bandwidth we are getting. Now after that, so our main focus was not isolation improvement in this work. So that I'll be I'll be mentioning that what was the main focus of this work. So after that development, we have tested the other antenna characteristics like gain and efficiency, these things. And what we have getting that gain is not very high here. So it is somehow around maximum 7 dBi gain we have obtained, and efficiency is also around 75%. We are getting the measured efficiency obviously, and then we have plotted the pattern, and quite obviously it is the omnidirectional pattern we are getting, or bidirectional like figure of 8 in case of E-plane we are getting. Now we calculated the other MIMO parameters like diversity parameters, ECC, envelope correlation coefficient, diversity gain, then channel capacity loss, then torque. So all these parameters are calculated, and we have identified all these parameters are within the threshold level. So ECC is very good. That is actually we are getting an if you, I believe that all of you know that this concept of ECC and other things, I am not discussing it again. If you require, we can discuss it obviously later on. The DG is we are getting around 10, and DCC is below 0.01. Then we got the other parameters like torque, we are getting below -10 dB within the entire frequency band. And also we got the mean effective gain that is in between -4 and -12 dB for all ports. And the channel capacity loss is 0.5 beats per second per hertz. And from these parameters, we are somehow satisfied with the antenna performance. It can be considered. Uh, Now, after that, uh, so this is the summary table that I have mentioned, the antenna performance summary table. Now, after that, we have developed one frequency selective surface. And our plan is to utilize it as a superstrate over the antenna. So it will be passing some signal, the desired signal, and it will be blocking the other spectrum, which is non-desired. And by this method, it will be actually, we are utilizing it for a gain augmentation. That was the primary focus. And at the same time, we have also developed a meta surface that I'll come to that part after this. So this bandpass FSS is basically developed using the same Rogers 5880 substrate, which is having a permittivity of 2.2 and thickness of 0.5 mm. This FSS unit cell, you can see it that it comprises of two square slots of different dimension in the top layer and in the bottom layer. Shape is same, but the dimensions are different. And uh, there is a presence of a square shaped patch uh, in the top layer, and that makes the transmission characteristics of the FSS higher. You can see the different performance metrics of the FSS. Here we are getting the desired passband, which is minus uh, desired stop band, that is a -24 to -30 is the pass band, and rest other spectrum is stopped because that part we are not utilizing for our 5G FR2 band. And we have done the ECM characteristic analysis also, and these are using ADS tool, and these are the lumped element values for this particular design. And then we have considered the third design, that is the meta surface. So this meta surface is actually printed on a Rogers, not Rogers TMM4 substrate. Hello. Yeah, am I audible now?
Yes, you are audible.
Okay. So this in this slide, you could see the third layer, that is the meta surface layer we have printed over a Rogers TMM4 substrate. And this meta surface is having 5 distinct band coverage. So this the target was to realize the 5G FR2 bands. These are from N to NR 257, 258, 259, 260, 261, and 262. Out of this, 5 spectrums are targeted, and with a very high Q factor without losing any valuable spectrum, we are successfully developed to design this meta surface so that the properly 5 FR2 bands are actually we are getting the response of S21 response, that means the stop band response, those 5 bands. Then uh, its circuit model was also developed, and the lumped element values are calculated using ADS, and then it was verified using the mathematical numerical analysis. And then what is the main feature of this work is that it is having almost all angular stability and polarization insensitivity. So in both TE and TM plane of polarization, from all the degrees, for all the degrees of incidence, we could see that its transmission characteristic is not changing. So that's why it is giving a polarization stability. And its phase of S11 we have also studied. So it is it is linearly decreasing, but not entirely linearly decreasing, matlab not constantly linearly decreasing. It is partwise linearly decreasing, and it is quite accepted. The reason is that, or it is not a wideband meta surface we have developed. We have developed the meta surface over some particular narrow band, narrow FR2 bands, and within that band it is linearly decreasing. So that also gives us the idea that it can be used for gain augmentation. Then we have calculated the shielding effectiveness also, and the shielding effectiveness is also proper in this work for these 5 distinct bands. And this work is already, the patent was granted. So just in this year, a couple of months ago, this patent was granted for this particular meta surface design. Then what we have done, this is one interesting things you can consider, that here the schematic, if you follow, we have developed these three things, and the antenna is the MIMO antenna is at the middle. And just please don't consider this. This is a old picture actually. So the connectors are SMA connector. However, if you see the uh, actual figure, so I just forgot to replace it. So this is the K type of connector which is actually utilized. So this K type of connector is utilized for in between 18 to 40 gigahertz. That is amphenol connector. Uh, so just pardon me for this utilizing the old picture. Okay, so here the antenna element is at the middle. At the top of the antenna, we are having the passband FSS, and at the bottom of the antenna, we are having the meta surfaces. So we have calculated the optimized the the distance, air distance between the antenna and FSS, as well as antenna and meta surfaces. So the range is from 2.5 to 3.5. So if you vary the distance from 2.5 mm to 3.5 mm, it works perfectly. So we have kept it at 3 mm. And considering the thickness of the materials, the overall distance is 7.38 mm. So the 7.38 mm is perfectly matchable if you compare it with a smartphone. So our plan, the way we have proposed to implement is that in that RFIC circuit, additional to that RFIC circuitry, we can place the antenna. Then just below beneath the display, we can place our FSS, and at the top of the casing, antenna casing, back casing, mobile back casing, we can place the meta surface. So it is not occupying any extra space. It is just utilizing the available space. And then this work was patented, not a design patent, utility patent also. The both are utility patent as a 3-layered antenna module. You could see it was granted within 6 months. And then we have studied the characteristics of the all these three elements in together. So what we have seen that it gives the 5 distinct band coverage very properly. So within FR2, it is working perfectly. Then second thing is that the transmission coefficients also, it gives a very less than minus 25 around the interport isolation, minus 25 dB interport isolation it gives. So isolation also improved little bit, but the best part we are getting is in terms of gain. So the gain previously, if you can remember, we have reported the previous gain was around 7 dB, 7.5 or 7.3 dB, which is now improved to 11.8 dB by utilizing this meta surface. So the gain augmentation is also achieved. And other parameters, other MIMO diversity parameters, the ECC, TARC, DG, mean effective gain CCL, those are not changing. Those are within the acceptable range. So that's why the overall dimension is also very much incorporatable or deployable within a mobile handset. So that is one concept we have developed to integrate the meta surface, mobile antenna, MIMO antenna, and the FSS as a superstrate for mobile communication, 5G FR2 band mobile communication. Then these are the gain plot that already I have mentioned, that gain improvement was there, and the efficiency was around 80%. The measured efficiency was around 75%. So efficiency is not that much changing. It is a little bit, but gain is the main improvement we are obtaining there. Then second work I would like to introduce or discuss, that is on GPR antenna development. So here you could see we have developed one table fan shaped antenna, which is basically a bow tie, developed from a bow tie antenna. Bow tie antenna is a derivation of conventional biconical antenna, dipole antenna, that has planar compact profile, light weight, and wideband coverage. So biconical dipole antenna is a solid antenna, but bow tie antenna is a planar antenna that is developed from that biconical antenna to get the wideband responses. Now we need to remember one interesting things that I forgot to mention during the discussion of GPR, that our antenna bandwidth should be high, but the band should not be in a higher spectrum, like a higher radio frequency wave. It should be started as low as possible. Like if we can start it from 400 megahertz or even 200 megahertz, that will be very helpful. Now, all of we know that if we are willing to tune the lower frequency, obviously the challenge will be to keep the dimension compact, because we cannot go for a very big dimension, because ultimately we have to use it in using a portable GPR device. So keeping antenna dimension compact is a very challenging task in GPR, because if what will be the problem if we tune at a higher frequency? The issue is the attenuation, because everywhere in all the materials, like in ground surface, there will be some water will be present. Water molecules will be there, or air bubbles will be there. So because of these water molecules or air bubbles, the signal will be attenuated, and this attenuation coefficients actually increases with increase in frequency. So if we go for higher frequency operation, obviously the attenuation will be more and the penetration will be less. So the main challenge in GPR is that we need to tune the lower frequency, but at the same time we need to keep the antenna compact. So that's why we have developed this antenna by controlling the flare angle. And what we did this is one bow tie arrangement, spiral shaped bow tie. This is the conventional bow tie. From conventional bow tie, we have developed the spiral bow tie, and then we have taken the orthogonal placement of two such dipole. So by ensuring this orthogonal placement, we are actually covering all 360-degree coverage, radiation coverage. And then we have added one cap, this capacitive cap. Now, why this capacitive cap is incorporated? Because if there is a metallic cap and there is a metal here also in the spline shaped arm, in between this metal we are having dielectric. So metal dielectric metal, this gives a capacitive effect. So this capacitance is created here. Further, there is an annular ring was created, and the antenna patch is embedded within the annular ring. So there is again a capacitive effect is created in between the top metallic cap and the annular ring. So this capacitance actually helps to resonate the frequency. So it widen the bandwidth. So to broaden the bandwidth, capacitive loading is very much crucial in case of GPR. So okay, so the antenna design equations are actually given here. The paper is under review in the IEEE transaction on geoscience, uh, and but the patent is already published, so that's why I am able to show it to you. So this antenna's dimension is not very big. It is having a dimension of around 0.3 lambda, and in terms of absolute dimension, I think it is. Let me check whether its absolute data is there or not, but I think it is somehow around 75 millimeters, something like that. So this is the fabricated prototype of the antenna. It was fabricated on FR4. The reason is that it is actually the lower band we are actually targeting. So FR4 can perfectly work up to 6 or up to 8 gigahertz without any such major disturbance. So uh, here, after developing this antenna, we have developed the FSS also, and this is FSS unit cell you can check. And within this unit cell, there are 4 by 4, 16 patches of hexagonal patches, and which are added within a square slot, a square strip, and the square strips and the patch are interconnected. And this FSS is developed on a Rogers RO3010 substrate. And altogether, uh, this antenna, GPR antenna, its placement should be towards the ground. So that means plus jet direction will be towards the ground. And at the back of the antenna, we have placed this FSS. And the purpose is very same. Just to augment the gain, I'll explain that physics behind gain augmentation using FSS also. So when we have tested the FSS, we have seen that it is perfectly covering the bandwidth, the desired bandwidth, that is from 0.6 to more than 6 gigahertz. And the FSS is also analyzed using the equivalent circuit model. And this is the placement of the antenna and FSS. And when the antenna and FSS are combinedly tested, what we have seen the bandwidth coverage is perfectly aligned with the single antenna system. So addition of FSS does not changing the antenna bandwidth, which is very crucial to ensure. And this is the about antenna FSS performance analysis. We are getting a much improved gain, which is more than 10.5 dBi after addition of the FSS. Otherwise, it is less than around 5.5 dBi. And if you see the pattern, also pattern, the back scattered wave is reduced. So back radiation is, less compared to the desired front lobe radiation. So now this is the placement. This is the actual work that we have carried for our experiment. So this is actually this work was sponsored or funded by TechSmin. So TechSmin funded this work, and we have developed one wooden cart. Within the wooden cart, so we are not losing any extra space just for addition of the FSS. Uh, uh, Below the wooden cart we have placed the you can see here this type of hollow cavity kind of things we have developed, and that's just below beneath to this portion we have attached the antenna unit, and behind that we have placed the FSS. So there is no additional spaces required to keep the antenna. Same space we can utilize it, and then these things are connected to the source module. A signal generator is the source here, and then power meter at the receiver end. All are USB power meter and USB signal generator. Both are within the frequency range, some 10 megahertz to 9 gigahertz. Then we have used, and the power meter is up to 12 gigahertz. We have used Latepanta board. Latepanta is the pocket computer, like you can see. Delta 3 Latepanta board we have utilized, and display is connected there. We have interconnected all together, and this is the U blocks receiver. I will come to that part after discussing the GPR part. So this is another novelty of this work. I will come to that part. So U blocks is also utilized there, and then we have tested it. We have dig some portion in the ground playground, and we have placed some metallic strip there, aluminum. We have stripped aluminum sheet, and then we made an array of 6 feet by 10 feet for C scanning. So in GPR there are three different type of scanning are possible: A scan, B scan, and C scan. A scan means point scan, so that at a particular point if you are doing your GPR operation, that is called A scan. B scan means if you are doing your particular operation through a specific horizontal line or a vertical line, then that is called B scan. So then C scan. C scan means it is in a matrix formation. That means you are moving from this side to that side. So this is horizontal movement. Then you are moving vertically, then again horizontally, then again vertically, then again horizontally. So if you move in that fashion, that is the C scan operation. So we have performed C scan at some equispaced distances and using this cart. And then at the let me just explain it a little bit briefly. So this, if you see that wooden cart, it was operated manually, and it was prepared to carry the subsurface imaging operation as well as location precision. Now we have connected two similar prototypes of the antenna with uniplanar FSS, where FSS is the reflector at the bottom of the card, and we have you can connect either VNA, dual port VNA you can utilize, or both the port of the VNA can be connected, or here instead of VNA we have used one signal generator at the transmitting antenna and power meter at the receiving antenna. Then we have developed this field for testing, and we have buried the metallic objects, aluminum sheet in different thickness levels. Then the signal source, uh, you can make it in two way. Either it can be continuous wave generator, or it can be a Gaussian monocycle generator. So for Gaussian monocycle generation, you need a VSG, a vector signal generator. So or pulse generator simply can also be utilized. So anyway, if you use continuous wave generator, your resolution will be little bad compared to the continuous the Gaussian pulse. So we have started with 600 megahertz, and because well, we need to keep the transmitting frequency low as possible to avoid the attenuation. And transmitting power was kept at minus 10 dBm. And the stop frequency was set at 3 gigahertz. and IF bandwidth is 22.4 gigahertz, and we have taken a frequency step size of 10 megahertz. The receiver antenna which was connected to the power meter, it actually collects the received data continuously for a preset time period. And we have considered multiple transmissions so that because we do not have any real-time backscatter noise removal, we have applied a backscatter noise removal SMD process later on. So the transmitter and receiver antenna were placed just in proximity to the ground surface, and after connecting the data points, we have kept a gap of 6 inches between 2 points. The data was collected and it was fed to the MATLAB simulator, and then in the MATLAB we have run some code to do the SVD, singular value decomposition. Using SVD, we are mitigating the coupling between the transmitter receiver and the noise removal. These things we have taken care. And the received signal with highest power at all transmission for any particular location is stored. And that was processed further to ensure that we are getting maximum signal to interference ratio. So that is nothing but a match filter approach. So if you studied match filter in digital communication, it will be easier for you to understand that we have implemented similar approach like a match filter so that we can ensure the maximum signal to interference ratio at any particular signal receiving point. Now we have taken 4 different operation in 4 different measurement environment. The first category is that we are having variation in antenna with and without FSS based reflector. So in one case we have attached antenna only. In another case we have attached antenna with FSS. Then we took the variation in the soil type. In one case we have used just like a dry soil that I have shown you. So this is completely dry soil. We have utilized this dry soil. In second experiment, we have put some water and tried to get the result in the wet soil. Because obviously in presence of wet soil, our performance will not be as good as in case of dry soil. So here also in the result, you can see when we are having only antenna in dry soil, the result is somehow moderate. When the antenna and FSS is connected, we are getting a very prominent scanning result. When only antenna and wet soil, the result is not at all very good. But when FS is connected, somehow we can identify the location. So this is one realistic experiment we have carried using our wooden cart. Then I would like to discuss the second part that was incorporated in this case. So here we have utilized this is the U-Blocks receiver. That U-Blocks receiver is connected with a ANN patch antenna here, and that is basically a multi-GNSS rover. It is used here. So if you consider to begin this experiment, we have set it first the base station. So the base station was actually there in our satellite navigation laboratory at NIT Jamshedpur, where a compact, low-cost, dual frequency L1 and L5 frequency multi-GNSS receiver module was used, and it was connected to U-Blocks JDD-F9P, which is connected to Skytrack survey grade antenna. So this Skytrack survey grade antenna is connected to the U-Blocks receiver at the base station. And then in base station, we first logged the data using Articleap software, minimum for 24 hours to identify the latitude, longitude of this particular geolocation of the base station. Okay, so that is the first step. Then at the receiver, where we are using the data collection for GPR, there we are having the rover unit. In the rover unit, we are again having U-Blocks receiver, which is connected to the ANN patch antenna. And instead of laptop, we have used here that Latebanda board, Delta 3 Latebanda board. And then these data are collected. At least we need to collect the data for half an hour. 30 minutes data collection is required. So after 30 minutes data collection for each point, we need to then we can calculate we can identify the coordinate using multi-GNSS environment. In our case, we are getting 3 different GNSS constellation. One is the GPS all of you know, then Galileo and QZSS. QZSS is the Japan constellation, and Galileo was also there, E1 and E5. So using these 3 multi-dimensional GPS, we have collected the data for half an hour duration at each point. Then we have utilized a post-processing software that is nothing but MATLAB. In MATLAB, we have processed the data, and this method is called PPK, post-processing kinematic. Using post-processing kinematic, our data were the robot data, matlab, this receiver stations data were calculated, and we have identified the location. Now, this location data, then we have calculated using different model. Uh, so I am not going in detail into the process. If you are actually interested or willing to know it, I can discuss it. But just give you the brief idea. That is my main target here. So then we have done the three different calculations we have taken. One is 2D RMS. 2D RMS means distance root mean square. Then CEP method we have applied. That is circle of error probability. Then SCP, spherical error probability. Then MRSC, mean radial spherical error probability. So all these different error calculation also we have carried, and ultimately we got our result. So we can show you the results also. Here are the results, and this is the real distance between any two geolocation, and you can see the precision in meter, that is 0.01 or 0.2. So that is in centimeter scale we are getting the data precision. So one can simply ask that instead of GPS, why we are using multi-genesis? Because GPS is much easier to implement. But we know in GPS or in Google Map everywhere, the location precision is up to 10 meter. So 10 meter location error could be there. But in case of GPR, the location should be very much, accurate. So its precision should be high. If we are considering at up to 10 meter error, then there could be a very high chances of erroneous, outcome. So that's why we need to go for PPK. And the advantage of PPK is that it is post-processing. So even if in your geolocation internet is not available, you can carry the experiment and later on you can calculate it. So that's why you have considered PPK. And in PPK, we are getting centimeter level precision. So it is very much beneficial compared to GPS. So this is the multi-GNSS we have adopted there. And this complete work was already published very recently for the patent, and it was also communicated. So that is under revision. Now, the last part I would like to explain. So these are some patch antenna. I am not going to explain because it is all of we know that how to develop patch antenna and how to design it. So just for your idea, so we have developed so many different patch antennas initially, and all are having it could be electrically very small also, like 17.5 by 14.5 centimeter dimension. But in all cases, the main drawback is the gain value is very small. So it is somewhere around 2.2 to 4 dBi or 2 to 5 dBi. Within that range, we are getting the gain value. So how to augment the gain of such wideband antennas, patch antennas? So that can be done using FSS. And second type of patch antenna, as I mentioned, for UWB application, that is the filter, where the filtering characteristic is incorporated within the antenna performance, like so that it can tune some frequency, it can avoid some frequency. So within that very wideband range, there are so many interfering applications are already there, like WiMAX, that is a 5G standard, then WLAN standards, Wi-Fi 5.5 gigahertz Wi-Fi. So everything is co-located with the commercial UWB. So to reject those frequency, we can go for filter design. So we have done some filter designs also in different work using SRR strip, SRR slot, then a 3-layered SRR embedded at the back of the antenna. So these are some methods we have applied, and we have developed very good filtering antenna, where filters or notched antennas, where we are getting perfect bandwidth coverage except the interfering zone. So you could see from the VSWR plot that it is perfectly eliminating the interfering signals. And we can explain it from the surface current also, but these things are very, not a new concept. These things are very well-known concepts. Now, just what I would point out here is the gain augmentation part. So for gain augmentation, we can design a combination of passband, stopband, or a single FSS also. So initially we have started with dual band FSS, two FSS elements, where the top layer is the passband one and the bottom layer, both stop band basically, but the top layer is actually resonating at two distinct frequency, and the bottom layer is resonating at the middle frequency. And when both are integrated with an optimized air gap, it is covering the 3.1 to 10 gigahertz wideband responses. And here also you can see the phase response is linearly decreasing. Now, this is another single aperture type of FSS we have developed. This also having the linearly decreasing profile. Now, every time I am mentioning the linearly decreasing profile, why it is significant, I'll discuss just after a couple of slides. So this is another FSS design where again the bottom and lower layers are having different configuration. uh, when we are adding this kind of FSS beneath the antenna, the stop band FSS, then we are getting a gain augmentation without changing the antenna other characteristics like bandwidth, efficiency. These things are not changing, only the gain augmentation is we are getting. Now, how these things are happening? So you can understand this thing from this figure. So my configuration is that we are having the antenna element. After some free space, we are having the frequency selective surface layer. So this is the frequency selective surface layer. Now we are having one front lobe radiation and one back lobe radiation from the antenna. Now the back lobe radiation, when it is reflected from the FSS, because it is a partial reflective surface, when it is reflected, because it should be, the frequency should be matched, only then it will be reflected in that frequency within the stop band. When it is reflected, if your S11 phase response is linearly decreasing, then this reflected wave will be having similar phase just like to the direct wave. So your actual radiation towards broadside is having some phase, and this reflected wave will be having the similar phase when it is linearly decreasing phase profile you are having of the FSS. And then these two signals will be added together because they are co-phased. So they will be added constructively, and you will be getting a boost in the positive in the forward plus z direction, in the desired direction. So your radiation will be enhanced, or obviously your gain will be augmented. So that is the physics behind addition of FSS. Now, some people claims that why only FSS? Why not metallic reflector? Because metallic reflector does the same thing. Instead of considering so many design calculations, so many design things, you just replace the FSS with a metal, and they will be getting the reflection. They will be getting that similar advantage. So that question is valid, but my submission is that if you use a metal reflector, the problem is metal reflector. That distance is fixed in case of metal reflector also, and the metal reflector will gives you the energy enhancement or boosting over a narrow band. But in most of my application, we are covering ultra wide band. So whenever we are covering the wide band responses, metallic reflector cannot be utilized. It can be utilized, but every time you need to change the spacing. So that is obviously not easily possible to change the spacing every time, considering the radiation frequency. So that's why we are using here the FSS or any PRS surfaces instead of metallic reflector, which is much more beneficial compared to that. So similar kind of examples, we are having many more. Now, this is the last part I'd like to discuss in my today's lecture. That is some GPR applications. So in GPR application, first we have tested the antenna and FSS performance in GPR environment when it is placed in close proximity to the soil. Then it's S11 and other characteristics, group delay and the dispersion characteristics are studied. And only when the antenna performance is satisfactory, then we go for the GPR experiment. Uh, so similar kind of experiments we have conducted for different types of antennas. And then this is one work. The lower work is not mine. This is some other groups, they have done this work. So they have done this work based on a simulation environment within a metallic, three metallic objects they have kept within a textile box. And then they have done the C scanning, and they have plotted it in MATLAB. Following this mechanism, we have tested it experimentally, and we have also got the results. And we have seen that when FSS is utilized, obviously our result is much better compared to only antenna when utilized. So FSS gives you better result. That means it gives you, it allows you to go a much deeper calculation or penetration of the GPR device. So again, we have tested it in another environment also. So this is in another environment we have tested it handheld GPR using. Here also we are getting a much better result. You can see clearly when the FSS is utilized, the scanning result is much better compared to the without FSS only antenna. So thank you. I believe somehow I managed to complete within the stipulated time. So thank you.
Thank you very much, sir. Sir, may we ask some questions?
Sure, sure, sure. Yes, please.
Participants, you are requested to ask questions, your doubts you can ask or raise your hands. Sir, one question is there from my side only that, sir, actually, CPW wideband antenna I have designed, sir. Now,
Okay.
for increasing the gain, sir, some papers claim FSS as a superstrate and some papers claim FSS as a used beneath the proposed antenna to increase the gain. So, sir, how to decide whether it should be used above the antenna or below?
Okay, this is a very common question and a good question, obviously, for all the people who are actively involved in such experiments. So, because I also do have similar questions during my journey of my PhD. So, the thing is that FSS can be used as a substrate as well as substrates like a beneath the antenna, as you mentioned perfectly. Now, when you are using a substrate for gain augmentation purpose, at that time you need to allow utilize it as a passband FSS just to allow that particular band, and the other part you can act as a stop band. So it gives you more like a radom kind of things, and at the same time it augments the gain because it is a partially reflective surface. So it's a semi-transparent layer basically. It is the waves which is coming, it is blocking, but some part it is getting, and that some part is confined, so confined in a particular direction. So when it is confined, its energy will be confined. So when the signal is confined, energy is also confined. So that's why its energy boosting is there. So that is the strategy in case of when you are acting as a superstrate. It is just like a Fabry-Perot configuration. So if you study the Fabry-Perot configuration, that is also similar to that a little bit. But when we are using FSS as a beneath the antenna, in that case, when my backscattered wave is coming, and that backscattered wave is reflected from the FSS top layer, and that is if the FSS is having linearly decreasing phase, it will be co-phased and it will be combined constructively, and your gain will be improved. So both are possible, but I preferred personally to go with the beneath the antenna because it gives me much more flexibility. And there is another reason also, because mostly I used it for GPR applications. So in GPR applications, actually it application specific. That is my point I want to tell you. So when I placing my antenna towards the ground surface, so obviously when I placing my FSS beneath, the advantage is that the FSS can be kept by the wooden surface. But if I place it just above the antenna in this direction, then I need another some structure, and that structure will be obviously wooden. So that can further block your antenna original radiation. So that's why it can disrupt your original radiation as well. So based on this configuration, based on your application, you can decide both are possible, but obviously it is based on your priority and your design aspects. I have shown both the things, like in case of that mobile communication application, we have used FSS also as a superstrate, but in case of GPR, mostly we have used as a substrate or beneath the antenna.
Sir, can I keep distance between the unit cell different, not the same?
Yes,
Between
this type of actually, yes, there is again a concept like nowadays digital meta surface concept is also there. So here, when you are configuring different unit cell, that is also possible. And when you are designing uh, keeping different distance of the unit cell, that is also possible, but conventional design does not allow. So if you go for digital meta surface, like some block, you are defining that block as a zero operation, you are defining another block as one operation. So to get the 0 and 1 switching, you can change any design orientation. Either you can change in terms of your gap, or you can change in terms of shape, or you can change in terms of pattern itself. The unit cell altogether can be, matlab, like in polarization converter, it could be 60-degree aligned in that side, then another one could be 60-degree aligned in that side. So all these things are possible. There is no strict rule behind to say ki you cannot do these things. You are allowed to do, you are allowed to experiment, but you have to explain, justify your your design with proper physical meaning.
Sir, one question from the participant, that what should
Yes,
be
yes,
the
I have seen it, and that is a very prominent question, and that's why I have highlighted many times ki my meta surface or my FSS are not taking any extra space. That statement I repeatedly multiple times I have given. That question is very valid, and it was multiple times it was asked by the reviewers also. Ki somehow you have designed some compact antenna, very small antenna, and you have utilized a very big FSS surface, and you are claiming my design is compact, but actually it is not compact, because you are considering FSS also, and that is having a bulky configuration. And if your aerial distance is much more, then how it becomes a compact? Because you need to consider the overall dimension. That is true. It is all about your fitting placement. So if you can remember that I have shown in that mobile phone application, where it is not taking any additional space. Although you can say ki there is a 3 mm gap, but that much gap is always there. Some 2 millimeter or 2.5 millimeter gap is always there in between your uh, RFIC circuitry and in your display. So I am not I am not claiming any additional space for my FSS or meta surface. I'm just utilizing their space, but their configuration I am fitting my design. So effectively, my size is not increasing. Effectively, my size is as it is. So that type of innovation you need to respond. So your answer is very valid. Question is very valid. It is true. When you are using bulky FSS or bulky meta surfaces, obviously you cannot claim it is compact, but it's all about your strategy. You can place your things so that this additional, because your backside is always there. You will be wooden. We can utilize it for the place of my structural space place for my design. So I'm utilizing the available space, and I'm fitting my design within the available space. Uh, is it clear, or shall I?
Yes, sir, it is clear, sir. Uh, Sir, like you have used a test bench as a textile material for the GPR testing. So what all
So there is a miscommunication. If you see that slide, or whenever I'll be sharing, you'll be seeing that that is someone else work, and they have utilized it in a simulation environment. They have not done any experiment. It is Abdullah and their group. They have done that work from King Fahd University. So in that work, they have used a textile box. So what they are claiming, suppose you are carrying some unauthorized things within your bag or something like that, then they can detect, that can be detectable using their scanner, something like that. But what we have done, I have done mostly, that is the X-Men project. Similar experimentally. So textile non-metallic, this is uh, and we are metal. Then there is any more questions?
Sir, one more question from the participant. Is it
Yes.
any rule that distance should be lambda by 4?
Uh, the fundamental distance that is taken, because what the principle I have discussed about the backscattered radiation and its reflection and then co-phased. That is based on the lambda by 4 distance. So that you can go to lambda by 4 or in any order of lambda by 4. But practically what we need to do, you first find out the lambda by 4 distance, then you take some jump. Like if your lambda by 4 is 25 mm, let it be. Then you calculate 20 mm, 21 mm, 22, 23, 24, 25, 26, 27. So some set of distances you can calculate. You can go for different iteration, and then you need to find out the based value. Now, based value, how can you claim? It can be of two way. You can claim it. One is based on your S11, and obviously the second one is the gain. Because gain augmentation, if it is your primary focus, then obviously you have to find out at what distance your gain is maximum. But what happened when you're minimizing the distance, then the coupling will be more between your antenna structure and the FSS structure. So at that time, your S11 might be disturbed. So you cannot disturb your original antenna's S11. So bandwidth need to be intact, or it can be disturbed up to some allowable limit. But obviously, you should try to get maximum gain without disturbing the bandwidth, impedance bandwidth.
Okay, sir. Thank you, sir. I think no more questions are there. Participants, if you have any question, you can ask.
Yeah.
Sir, I think only these many questions are there.
Okay.
Thank you very much, sir. We from EICT Academy MNIT Jaipur and Department of Electronics and Communication Engineering MNIT Jaipur, sir. Thank you very much for accepting the invitation. The session was very much fruitful for all of us. And once again, thanks a lot for accepting the invitation, sir.
Thank you. Thank you, everyone.
Thank you, sir.
Okay. Thank you. I'm disconnecting.